Let us now talk about an example that involves a rational function. So the first thing to do, if you see such an integral, is to classify its integrand as a rational function. Specifically, as you can see, this is an improper rational function. Okay, so once you have determined that, the primary choice you want to make is whether you want to go ahead and use the partial fraction decomposition in order to integrate this, meaning you apply long division, then you have a proper rational function to which you apply partial fraction decomposition. Or perhaps there is an obvious u sub to be used. Now, in this case, this is indeed an example that requires partial fraction decomposition. So let me note this. First, you want to apply a long division. And then, once you did that, apply partial fraction decomposition to the proper rational function. Now, what do I mean when I say that there may be a trivial or a simple u sub hidden here? So I trust that you know how to apply partial fraction decomposition now that we have dedicated an entire section to that. So what is a simple u sub that may arise in such examples? Well, I want you to observe that in its current form, this example does not have any interesting u subs hidden in it. Now, what would happen if I changed the numerator of this example to be something of the form 3x squared minus 6x minus 10? If I had that, or perhaps some multiple of it, so suppose I don't have this guy, but instead I have, say, 6x squared minus 12x minus 20. So if I had this numerator, then instead of applying partial fraction decomposition, you would be much better off if you just noticed that the numerator is 2 times the differential of the denominator. And the correct way to proceed would be to set u equal to the denominator. So this is something to keep in mind. Whenever you have a rational function, say, of course, you have this powerful universal method of reducing this expression to partial fractions and then integrating them. But there occasionally may be shortcuts that you want to use in order to save time and effort on a test. So, such as, for example, with this modified numerator, the optimal strategy is to use u sub with u being the denominator, because then the numerator is just 2 times the differential of u. So I leave example 3 for you to complete. Now, in example 4, let us think about this expression here. So first, there is not much here in terms of simplification. Let us think about some easy u subs. So this is an expression that contains square root. So one way to proceed here would be to try the substitution that we use whenever we have a radical in our integrand. So one way to proceed would be to set u equal to that square root. So this is the strategy, you know, may or may not work, but in this case, this approach actually works, and by using this substitution, you can then, in order to express dx through du, you would do u squared equals log x, and you would say that e to u squared equals x. And as a result, 2u e to the u squared du equals dx. And this is what you would use for dx, and using this line to express x through e to the u squared and to express this guy through u as we have in the first line here, you would actually integrate this expression successfully. A better approach, though, would be to use a simple u sub. Now, you may have noticed this already. If not, you should pause the video now and think for a second about any simple u subs that you may notice in this expression. Okay, so the simple u sub here is, of course, to set u equal to log x, because then, as I look at this expression here, it is precisely du, since du is dx over x. And so, using this u substitution, my integral becomes du divided by square root of u. And this is u to the negative 1/2 du, and this can be integrated as a power function in a completely straightforward fashion. Again, I will leave this to you for you to complete. I don't want to focus on these examples. They're just for illustration purposes of how to apply the general integration strategy. So here, in this case, we could apply the generic approach, which we can use whenever our function inside the integral has radicals, or we could be a little bit creative and notice that there is a straightforward u sub here to apply. Finally, I want to show you yet another example where simplification plays an important role and is very essential in completing the integral. So I want you to always keep your mind open to the fact that by using some suitable algebraic transformations, you often can achieve much simpler form of your integrand, and it will make your integration procedure much smoother. So what you want to keep in mind is simplify, always simplify the expression you want to integrate first. So in example 5, we are looking at the integral of square root 1 minus x divided by 1 plus x dx. So again, we are facing an expression that contains a radical. And one way to proceed would be to try to set, again, u equal to the square root of this expression here. So you could use the square root inside the integral to set for u, but then solving this relation for x will be rather tedious. Even expressing x through u so that to compute the dx in terms of du will be rather complicated, and this is really not the best way to go, even though you may get it to work if you're careful with your transformations. Now what we will do instead, so this is not the route that we'll take. What we will do is we will observe that this ratio here, this square root here, is the same as square root of 1 minus x divided by square root of 1 plus x. And so here we're basically using the property of square root that says if you are looking at the square root of a ratio, you may just as well rewrite this as the ratio of square roots. So this is what we're using. Now, in view of this representation, notice that we could get rid of at least some of the square roots by multiplying numerator and denominator by, say, this square root here. So we choose to do that because we have 1 minus x and 1 plus x under the square root. And so the product of these gives us difference of squares. And so what we'll do here now is multiply and divide by square root of 1 minus x. So I'm choosing the square root that sits in the numerator to multiply and divide by, because once I square this radical here in the numerator, I will have 1 minus x in the numerator, and I can split it into a difference of two expressions and then integrate them separately. So this is the primary motivation. Okay, so once I do that, I'll get 1 minus x in the numerator and square root of 1 minus x squared in the denominator, because in the denominator I have this radical multiplied with this radical, and so I'm using that, again, multiplication of two squares like that is the same as taking square root of their product, of the product of the expressions inside the radicals. Again, this follows from the properties of square root, and using those I conclude that I have a difference of two integrals Now, the first integral is of a standard form. It's standard expression for which there is a simple antiderivative, and you should know what that antiderivative is. So the first integral has closed form antiderivative that is one of the standard functions in our course, and you should certainly look at that handout on standard antiderivatives that you have under the Files tab on Canvas. So you may want to pause the video now if you don't remember what this is, the antiderivative, what this expression is derivative for, and check your notes, and then we'll proceed from there. Okay, so as you have found in your notes, this here has the antiderivative arcsine x. As for the second term, what I will do here is use a u sub. And so let me take this integral here and look at it separately. So using u equal to 1 minus x squared, I'll have du equal to minus 2x dx, negative 1/2 of which is precisely x dx. So this is the factor I have in my numerator. I will use it for the du of my new integral, of my u sub. And so I have minus 1/2 of du divided by the square root of u. So again, that means I have minus 1/2 integral of u to the minus 1/2 du, which is, so the antiderivative of u to the negative 1/2 is, so I have to increment the exponent by 1 to get u to the 1/2 and divide by this new exponent like so. And then going back to my original integral, my original expression, I will have arcsine of x minus this expression here, where I should change to x first though. So this will be minus square root of 1 minus x squared plus constant, and that is what I will be putting here. So I have put the plus sign here because of the minus here and the minus over here. And then this is in fact a different constant, so I am reassigning c to be minus c0. And this is how this integral is evaluated. So what I had to do was to basically multiply numerator and denominator by this radical from the numerator, and that simplified my life a lot. Now, instead of dealing with this complex radical here, I just need to deal with single radical that also has the standard form that we know is suitable for trig subs. So even if we couldn't find the antiderivative directly, as we did here with inverse sine, we would still we could still apply the trig sub in order to evaluate a more complex integral of this form. And so this is how algebraic manipulations were helpful in this integral.